In this video, I'm gonna talk about coroutines. In the first part of this video, I'm gonna talk about what problem Kotlin coroutine library sets out to solve, and I will also explain some terms you would come across when you start reading about coroutines. Before we dive in though, here's a quick disclaimer. If you don't have experience writing asynchronous code in any programming language, coroutines might feel a bit challenging at first. But don't worry, I'll keep in mind that not everyone is familiar with these concepts. Throughout this video, I'll also recommend checking out other YouTubers' videos to help deepen your understanding. Okay, first let's see what problem coroutines try to solve. To demonstrate this, I will show an app I have created. We're gonna run that app without using coroutines, and then we're gonna run it again, but this time we're gonna use coroutines. We are in the Android Studio and this is the app. So this is how it looks like. There are some cards and buttons and switches. I'm just aligning it. So we're gonna take a quick look at the source code, and then I have a function called counter. So this is our main app. So this counter has a lot of state variables, number, result, coroutines. These are used to keep track of values that change. I will also provide this source code in my GitHub repo. You can check that out. And I have a column, and inside of that column I have cards, some buttons, rows, buttons, and cards. So inside of those cards, most of the time I have just text. And then there's a class that contains some helper functions. So what are these helper functions? So what this app tries to do is it tries to find prime numbers. The reason why we're trying to find prime number is that I wanted a function that takes longer to run, so we can observe how our app behaves when something takes longer to run. So this is the function that we're gonna run, this find primes. So this is gonna run for a few seconds. We will see what happens. Now I'm gonna run this app. So this increment button increments the values of this number, and then there's this button find prime numbers that will call find prime numbers function, and then there's this status not ready. So when the prime number function is running, it says it's ready, and then when it's done, it says if it found the prime numbers. And then there is this use coroutines switch. We can turn it on and off. So this lets us use coroutines on the fly. So let's click on this button and run the find prime function. So when we click on the find prime number function, our app just crashed. Okay, let's run it again and do something else. So it's gonna crash, but before we do, I'm pressing increment button, but it's not incrementing. Let's do that again, but this time I'm gonna use the coroutines. Use coroutines, find prime numbers, and as you can see, the our app immediately changed to reflect that the prime number function is running. It's now saying loading, and then we can press the increment button. Let's just wait for this to complete. Okay, requested prime numbers were found. So what just happened? When we run a function that took longer to run, our app just freezed and crashed. So essentially what coroutines does is it helps you run long running tasks on your Android app. From this demo, we can see that without using coroutines, you can't call functions that take long time to run or return or execute. Before I tell you why we can't run long-running tasks on our app, we need to know some basics. So I'm going to start from the scratch. So first, let's start with the definition of coroutines. So what's a coroutine? Coroutine is an instance of a suspendable computation. It is conceptually similar to a thread in the sense that it takes a block of code to run that works concurrently with the rest of the code. However, a coroutine is not bound to any particular thread. It may suspend its execution in one thread and resume in other. First, I'm going to try to give a general overview of what these terms used in the definition mean, and then we can start learning about coroutine. Okay, I think a good place to start when explaining this term is what happens when you launch your app. So your app is part of something called Android Stack. You're gonna learn about Android Stack when you start learning about Android architecture. So here's an image that helps you visualize this stack. We have system apps and Java API framework, native libraries, Android runtime, hardware abstraction layer, Linux kernel, power management, all this stuff. So these are layers. Each layer uses the features of other layers in the stack. Your app is somewhere in this stack. Here's another image that shows you the Android stack. Here we can see that Android apps live on the top layer, and at the bottom layer we have Linux kernel. Okay, the key takeaway here is that Android is complex and most of its nuance detail is just abstracted away. I mean, we didn't even know that Android stack existed, and even though we don't typically interact with the lower layers, what we write using a higher level programming language such as Kotlin does lower level functional calls. So Kotlin kind of abstract away all of these details so that we don't have to worry about what goes behind. Next, there are a couple of things that happens when you start your app. Firstly, when you start an Android app, the system creates a process to run it. Along with this process, a main thread, this is also called a UI thread, is created. Although threads are a bit complicated, I'll just give you a general overview. I'm not going to explain them in detail. So what's a thread anyway? To be pedantic, a thread is just a sequence of instructions that can be executed independently. In the context of programming, a thread is the smallest unit of execution within a process. Typically, the instructions in a thread are in machine code, which the CPU can directly execute. You can easily check for differences between process or thread on YouTube. Okay, here's a video that talks about thread, process, and program, and some more concepts like parallelism or scheduler. You have been writing some code in Android Studio that will execute when your app reaches onCreate stage, right? This code runs on something called main thread or UI thread by default. The main thread's primary job in an Android application is to handle user interface and process events, such as user interactions and system messages. Now, as for how your Kotlin code is executed by the CPU, it goes through several steps. Write is compiled into Java bytecode, which is then converted into DEX format during the build process, and these DEX files are interpreted by the Android Runtime, ART for short. Android Runtime is part of the Android stack I showed you earlier. It acts as a bridge between your app and the underlying hardware. Android Runtime pretty much takes on the role of Java virtual machines, but it takes consideration of Android's unique constraints such as limited memory and battery. Art uses ahead-of-time compilation and just-in-time compilation to convert the DEX files into native machine code when the app is installed. The CPU then executes the compiled native machine code, performing the tasks your app requires. And that's pretty much the gist of how your Android app runs. I know this might seem like an extra detail, but since we were talking about threads, I thought it would be helpful to explain how your Kotlin code actually runs on an Android device. Here's a video that talks about Java virtual machine in detail. And here's a video that talks about Android runtime. If you are interested, you can check them out. Let's get back to our original problem. When running a long-running task in your app, we saw that it makes our app unresponsive to touches. This happens because of how main thread operates. To explain, I'm going to use flowcharts as an example. Flowcharts helps you visualize the paths of execution. Let's imagine a flowchart that represents a program such as this. This creates 3 variables and reads, compares, does prints or something. The execution of instructions here aren't always linear. Often it branches out. Some paths aren't executed and some do. It's because of loops and conditional statements. Now let's say the CPU needs to execute 12 lines of instructions on this path. In this scenario, the execution is sequential. Each instructions are executed only after the previous one is complete. This is known as synchronous execution, where tasks are performed one after another, blocking the program from proceeding until the current task finishes. And our problem occurs because of this. When the prime number finding function runs, the instruction to draw on the screen, like composable function calls, cannot execute because the main thread is still busy completing the current task, which is to find the prime numbers, and it's taking way too long. Android doesn't play nicely when you block the main thread. Its default response is to throw app not responding error, and it calls it a day. On a related note, you might wonder why composable functions are called for execution even when they don't appear directly after the prime number finding function in your code. That's because Android apps operate on an event-driven architecture. This means that instructions are executed in response to events, like a button click, rather than strictly in the order they are written in code. In event-driven systems, there's typically an event loop that listens for and responds to events. Android has an event loop too. When the main thread is created, Android framework automatically associates it with a looper class. Looper together with handler class maintains event loop in Android. I don't want to dwell too much on the inner working of looper, but here's the gist. The looper continuously checks something called message queue for events such as user input, lifecycle changes, or system messages, and processes them in order they are received. Handler is used for sending messages or tasks to looper's message queue. Android uses handler internally to send events like touch inputs, lifecycle changes, or sensor updates to your app's main thread. Let's get back to our original problem. You could say our long-running function blocks the execution of other function or tasks, so it's a blocking function call. To solve the problem of tasks blocking the main thread, we need to ensure that long-running tasks like finding prime numbers are executed off the main thread on a separate thread, often referred to as background thread. Java provides several APIs for creating and managing threads, such as thread, executor, and executor service. These APIs give you control over thread creation and management, but they also require you to handle the complexity of managing the lifecycle of threads, thread pooling, and task scheduling. This is a complicated topic, and I understand if you get confused here. And over the period, there were different approaches to solve the problem we're having. from creating a thread to callbacks, futures, or promises, what have you. Long story short, each of these has its own set of headaches. Some methods require you to manually create and manage threads, which can lead to significant resource overhead and make lifecycle management more complicated. If you ever used a callback based approach, you have probably heard of something called callback hell, where nesting callbacks makes the code hard to read and maintain. Programming languages like JavaScript now uses promise-based approach, which can make the code cleaner and more readable. This approach is considered a big improvement over the old callback style. Let's take a look at all of them to understand why coroutines are considered even better. Here I asked ChatGPT to write me a Java thread example where it tries to fetch user data, user posts, and user comments. In Java, we use threads to simulate some sort of like background task. So here, as you can see, it tries to create new thread every time we need to do some background tasks. Here we want to fetch the user data. It created a new thread. Fetch posts, new thread. Fetch post comments, new thread. On top of that, it's using callback. And it just straight out looks ugly. And then there's just this. This calls the whole thing. So this looks overly complicated. And here we're trying to fetch user data posts and comments using callback based approach. Here we have a function that takes a user ID and then a callback. So inside of this inside of this function, we have like 3 functions that are nested one inside of another. So the first function that's outside of this nesting is fetch user data. That takes a user ID and notice that how everything is nested. It's nested because all of these network requests are dependent on the previous request. And then we pass the result to the callback. So notice this indentation. So as the result of, as the new network call becomes dependent on others, the indentation becomes much larger and it looks ugly. Also notice the fact that the error handling mechanism is kind of difficult. So this is one approach, and the other approach is using promises. So notice that we're making the same 3 network requests. New network request occurs only after the previous one is finished, and then we can handle the error using try catch. I use JavaScript to demonstrate the callback and promises. Now I wanted to make the same 3 network requests using coroutines. We use the assessment functions. So just look at how nice just look at how nice and clean it looks. We're just creating 3 functions, and then we launch on a different thread. This is just more cleaner and much more readable compared to our previous attempts at solving the problem. When we talk about performing multiple tasks, you will often hear the terms concurrency and parallelism. While they sound similar, they are different concepts. Concurrency is about dealing with multiple tasks at the same time, but not necessarily executing them simultaneously. Parallelism, on the other hand, is about running multiple tasks simultaneously, typically across multiple processor cores. In this case, tasks are truly executed at the exact same time. To put it simply, concurrency can be achieved with a single core processor, but to achieve parallelism, you need enough processor cores to match the number of tasks you are running in parallel. With Kotlin coroutines, you can achieve both concurrency and parallelism depending on how you structure your tasks and thread pools. When I say tasks, I mean instructions like fetching data from a website or performing a computation. Coroutines make achieving concurrency much more efficient. Instead of assigning a task to a dedicated thread, you delegate it to a coroutine. Coroutines run within existing threads, and multiple coroutines can share the same thread, switching executions seamlessly. This is much lighter on resources compared to traditional thread management. And when a coroutine encounters a long-running operation like a network request, instead of blocking the entire thread, it suspends its execution. This allows the thread to handle other tasks or run other coroutines while waiting for the network request to complete. Once the operation finishes, the coroutines resumes from where it left off without any overhead of restarting the task. And that's why coroutines are great, because they allow you to manage concurrent tasks efficiently without blocking the threads or using excessive system resources. Anyway, that's it for this video. In the next video, we're gonna actually learn coroutines. Until then, see ya.